Hello everyone, welcome back to the YouTube channel Devotion of Knowledge. Today we are back again with our main stream of YouTube videos creation or content creation, which is problem solving. And today we are back again with our Leetcode daily problem. Our previous couple of videos were based on cybersecurity domain that I tried to upload, in which we covered complete advanced encryption standards right from basics to complete numerical we have covered yesterday. The only final video which was about example completes a 40-minute video, means those who are willing to learn AES in complete detail, they can check out that video in description or YouTube video channel or playlist. But right now, let's get started with a lead code daily problem. So okay, let's first understand what the problem is trying to convey. So, maximum candies allocated to k children. This is the main question. Let us read the question. You are given zero indexed integer array candies. Each element in the array denotes a pile of candies of size candies of I. You can divide each pile into number of subpiles. Okay, you can divide each pile into another subpiles, but you cannot merge two piles together. Okay, means given number of candies can be broken down into further parts, but the given candies can't be merged into some higher number of candies. Okay, so you are given an integer k. You should allocate piles of candies to k children. Okay, such that each child gets the same number of candies. Each child can be allocated candies from only one pile of candies, and some piles of candies may go unused. Okay, return maximum number of candies each child can get. Let us consider this example: 5, 8, and 6. So these are the number of candies that we have: 5, 8, and 6. Now we have to give these candies or divide these candies into 3 children. Okay. So what are the maximum number of candies that each child can get? Okay. Maximum number of candies that each child can get. Okay. Here it is clearly visible because 5 we can give to one child, 8 to another child, and 6 to third child. But no, it's not the case because each child gets the same number of candies. Okay, no problem. Same number of candies. Okay, sorry. Same candies. Now, in such cases, or in this case, as you know, we can't merge any two candies. No, it's not allowed. So 5 will be the only answer because each pile we will be allocating to each student. But here, 5 from this one, 5 from this one, and 5 from this one. So total maximum candies that each child can get will be 5. Okay. But the interesting example is this one: 2 and 5. Now, as you know, we can split the given candies into some number of parts. So if I split these two candies into one, I am also splitting this 5 into one. So total I can get only 7 candies, but number of children that we are given is 11. So it's not the case here. So we will be returning 0 as the answer. Okay. So let us understand one more example so that we can get more familiar to the problem. The example is, I would say, 7, 8, 4, 3, 3, 9. Okay. And I am saying that the number of childrens are, suppose, 2, 2, 4, 5, 6, 7. And okay, 7. Okay. Let's say number of childrens are 10. K equal to 10. Now, in this case, what is the maximum number of candies that we can give? Okay, 7. So, in how many parts we will be dividing this 7 so that we can give maximum number of candies to all the children given. How? Can you think of any approach? Okay, no. Here answer will be three. Let me explain why. Here, if we give three candies to each children, so seven using seven candies, I can serve two childrens. Three, and one will be remaining, but no worries. Similarly, using eight, I can also serve three childrens. Using four, I can give candies to one child. 3, 1, 3, 1, and for 9, I can serve three children. So 3 plus 2, 5, 6, 2 and 2, 10. So maximum answer here is 3. So if I give 3 candies to each children, means maximum number of candies that I can give to any child is 3. Okay. So can you think of any approach? Oh, the question is binary search. Approach is binary search, but let me explain why. Whenever such questions come with a keyword of maximum or minimum, I would say, or maximum of minimum or minimum of maximum. In first two approaches, maximum, minimum, minimum, maximum, just think for once. I'm not saying binary search will be the only approach, but just think for once. Can binary search be my approach? But if the case is of max, min, max, then sure, so it's the question of binary search only. For this, you can try questions like aggressive cows, minimize distance between gas stations. All these are kind of min max problems. But maximum minimum, just think about for 1 or 2 minutes that can the binary search be my approach? Okay, let us think in this case, can binary search be my approach? Let me erase these things. Sorry, just a couple of seconds. Okay. Can binary search be my approach? Okay, let us see. K is equal to 10. So we have to serve 10 children using this amount of candies. Okay. So for binary search, okay, we should have some particular endpoints or some conditions between which we will be solving the problem. So what is the minimum number of candies that each child can get? Minimum number of candies that each child can get. 1, yes or no? Let me explain. Case is like this, 3, 4. And k is equal to 9. What will you do in this case? These 3 candies, I have to divide all of them into 3 candies, and this 4 into 4 individual 1 candies. So the minimum number of candies that each child can get is 1. I think I'm making some sense. And what is the maximum amount of candy that a child can get? Max equal to maximum element of array. Max element of array. Why? Let's consider this case, and I have given you just k equal to 1. What will you return? This 9 will be your answer. Okay. So minimum number of candies that I can assign is 1, and maximum candies that I can assign to any child is the maximum element of the given array. Now let us think of binary search. 1 candy and here 9 candies. Okay. So if I give you some x number of candies, please make sure, if I give you some x number of candies and I ask you that whether this x number of using this x number of candies that each child will be getting, can I feed my given k number of children? Sorry, not children's, children. Let's make sure. If I am having this k candies that each child will be getting, each child, I am giving you x candies that each child will get. So how many child I can give candies using this 7? I would say 7 by x. Let me again repeat. Here answer was 3, so 7 by 3 was 2. So I can divide this much of candies between 2 children so that both of them will be getting same number of candies. So 7 by x, okay, 8 by x, 4 by x. So I will be getting some, let's say, count of children. How many children I can feed or give or divide candies in equal parts. Okay, so this is the case. count. So if my count is less than, suppose k, if my count is less than k, it means the number of candies that I was dividing or giving to each child are larger than the required answer. Because if my given amount of candies is higher, it means the candies that I am giving, if I follow that pattern, there are some children who are not getting the candies. So in this case, I have to reduce my value of k, or sorry, x. Let me repeat. Initially, I was giving 10 candies to each child. I was trying to give 10 candies to each child. And at last, I got count. Count is nothing but number of children who are getting candy. If the value of x is the candy that each child gets. So if count is less than k, it means there are still some children who are not getting candies. It means I have to reduce the amount of candies that I was giving to each child. In that case, we will be reducing our x. So can you think, by decreasing our value of x, I am eliminating my some search space. If this was the value x between 1 and 9, and if my count is less than k, it means I have to reduce the value of x. So initially my x was here, and if I am reducing my x, all this search space, it is getting eliminated. So it is binary search, because this portion of values is of no use to me, because count is greater than k for this case. So if it is greater than k for this value, then it will be always greater than k for all of these values present on the right side of the x. So in this case, if count is less than k, we'll be doing nothing, just high equal to mid minus 1, because we will be eliminating our right search space, and we will be searching for our answer somewhere left from the calculated x that we counted. Okay, okay. This is the one case. Now, what is the another case which is possible? Another case which is possible is count. It is greater than or equal to k. If it is not less than k, it is always greater than or equal to k. Yeah, sure. So what in that case? If count is greater than k, it means for x number of candies, I am able to feed children greater than k. Means I have satisfied given number of children that I was supposed to, even though some children greater than the given value, means some extra children I am also able to feed. So in this case, the number of candies, which is x, I was giving to each children is lesser than my requirement. So there is a scope for me to increase this value. If I, for example, I say x plus 3. So x plus 3, because x was able to feed my k children as well as some extra children from k. But in this case, I am only willing to divide candies among only k children, not more than that. So if x is able to divide candy in children which are greater than k, if I increase the value of k, I will be allocating more number of candies to each child. So in this case, if count is greater than equal to k, in this case, I will be just doing low equal to mid plus 1, because there is some scope for me to increase the number of candies for each child, and I can feed or satisfy more number of children, so I can get some optimal answer. If I search between this search space, for example, x is here, and this much of candies won't be of no use, because x for this x count is greater than k, so my answer will lie somewhere in this search space. So I will be just eliminating this half, and I will be just searching for my answer in this search space, and answer will also lie in this much of area only. So I think approach is clear to you guys. Let us directly head towards the writing of code. Okay. Oh, code is already written, but कोई देखना मत, हम scratch से code लिखेंगे. Okay. So let me zoom the screen. Okay. Let us say I will be returning answer equal to 0. What I told you, what is the minimum number of candies that each child can get? It was 1. What is the largest or the greatest amount of candies that each child can get? It is the max of all the candies. Okay. Yes. So now we'll be just iterating while low less than equal to high. See, I have not performed a complete dry run because I think you guys are mature enough to understand that how this binary search works and how at particular sort of index or point I will be getting my most optimal answer. Okay. Okay. So let us count mid equal to low plus high by 2. And for this particular amount of candies, we will be checking. Let us name it X because while understanding the question, we have uh, understood it using X. So let us understand, keep X here. And I will be just iterating to my whole array. I less than V dot size. Okay, spelling mistake. I plus plus. And let us also initialize one count variable, which will be keeping track of how much candies or how much children I will be able to satisfy, plus equal to v of I by mid x in this case. Okay, if the number of children set or child's number of children satisfied, if cnt less than equal to k, it means the number of candies that I'm assigning per child is great. So we will be doing nothing, just equal to mid minus 1. Okay, and in else condition I will be doing nothing, just low equal to mid plus 1. But here in this case, I was not able to feed or distribute candies among k children. But here I am able to. So we will be doing nothing, just we will be storing this particular index or this particular value in my answer. Okay, and we are supposed to return max. So if I am, we have to return max. So somewhere between 1 to 9, somewhere between 1 to 9, if I'm getting or satisfied for this value x, then in next search space we will be always searching here. So if some value is also satisfied here, then we will be storing answer again. So it is, there is no need to write max of answer. I think you guys are understanding what I'm trying to say. Okay, and return answer, and let's run the code. Low equal to I equal to mid minus 1. Oh, sorry, x. Okay, because binary says I am habituated to write mid, but here to get better understanding, I tried to use mid. Okay, let's compare that there is no mistake. Yes, because here as you can see, constraints are 10 raised to 7. So 10 raised to 5 and 10 raised to 7. So for if we consider every time that 10 raised to 7 value will be added, so 10 raised to 7, 10 raised to 5 times it will be 10 raised to 12. So it will be exceeding our limit of int, which is 10 raised to 9. So I think yes, now the code should run. Okay, let us submit the question. Solution. Yes, we have successfully beaten 50%. But I think this is the most optimal solution here because n log n is the final time complexity. Let us submit again. So Leetcode comparison is useless. So let us understand time complexity. Okay, so for this binary search, it will be always log of n. And for each log n time complexity, we are iterating through the whole array. So it will be n for this time and O of n for how many times? For the whole binary search. So O of n for each and every log n time. So it will be O of logarithmic of n, n star n log n. So this is the time complexity of this question. I hope the approach towards the question was clear to you guys, and that's it from my side for this video. We'll be meeting in the next video very soon. Till then, keep learning, keep hardworking. Thank you very much.